Bases. Let V be a vector space over a field F. Let little v and W be in big V, and JK in F. The expression JV plus KW is called a linear combination of the vectors V and W. We call the scalars J and K weights. Let's look at an example. Let V be the vector space R2. In other words, V consists of the set of ordered pairs A, B, such that A and B are real numbers. This is the vector space over R with the usual definitions of addition and scalar multiplication. Let V be the vector 1, 0, W the vector 0, 1, J equal 4, and K equal -2. We have JV plus KW is equal to 4 times 1, 0 minus 2 times 0, 1 equals 4, 0 plus 0, -2 equals 4, -2. It follows that the vector 4, -2 is a linear combination of the vectors 1, 0 and 0, 1 with weights 4 and -2 respectively. If little v and W are in V, where V is a vector space over a field F, then the set of all linear combinations of V and W is called the span of V and W. Symbolically, we have span VW is equal to the set of JV plus KW such that J and K are in F. Let's look at an example. In the previous example, we saw that the vector 4, -2 can be written as a linear combination of the vectors 1, 0 and 0, 1. It follows that 4, -2 is in the span of the set consisting of 1, 0 and 0, 1. Theorem 8.3. Let V equal R2 equal the set of pairs AB such that A and B are real numbers, be the vector space over R with the usual definitions of addition and scalar multiplication. Then span of the set 1, 0, 0, 1 is equal to all of R2. Let's prove this. First, let V be in the span of 1, 0, 0, 1. Then there are weights J, K, and R with V equal to J times 1, 0 plus K times 0, 1. So we have V equals J times 1, 0 plus K times 0, 1, which by the definition of scalar multiplication is J0 plus 0K, which by the definition of addition is equal to JK. Since J and K are real numbers, we have that V equals the vector JK is in R2. Since V in span 1, 0, 0, 1 was arbitrary, we see that the span of 1, 0, 0, 1 is a subset of R2. Now, going the other way, let V be in R2. Then there are AB real numbers with V equal to AB, which is equal to A0 plus 0B, which is equal to A times 1, 0 plus B times 0, 1. So we've expressed V as a linear combination of 1, 0 and 0, 1. So we see that V is in the span of 1, 0, 0, 1. Since V in R2 is arbitrary, R2 is a subset of the span of 1, 0, 0, 1. Finally, since span 1, 0, 0, 1 is a subset of R2, and R2 is a subset of the span 1, 0, 0, 1, we have that the span of 1, 0, 0, 1 is equal to R2. If V and W are in big V, where V is a vector space over a field F, then we say that V and W are linearly independent if neither vector is a scalar multiple of the other one. Otherwise, we say that V and W are linearly dependent. Let's look at some examples. The vectors 1, 0, and 0, 1 are linearly independent in R2 because for any k in R, we have k times 1, 0 is equal to k0, which is not equal to 0, 1, and k times 0, 1, which is equal to 0k, is not equal to 1, 0. The vectors 1, 2, and -3, -6 are linearly dependent in R2 because -3, -6 is equal to -3 times 1, 2. If V and W in big V, where big V is a vector space over a field F, then we say that the set consisting of V and W is a basis of V if V and W are linearly independent and span of VW is equal to all of V. Let's look at some examples. In the previous example, we saw that the vectors 1, 0, and 0, 1 are linearly independent in R2. By theorem 8.3, span of 1, 0, 0, 1 is equal to R2. It follows that the set consisting of the vectors 1, 0, and 0, 1 is a basis of R2. We also saw in that same example that the vectors 1, 2, and -3, -6 are linearly dependent in R2. It follows that the set consisting of the vectors 1, 2, and -3, -6 is not a basis of R2. We would like to generalize the notion of linear dependence to more than two vectors. The definition of one vector being a scalar multiple of the other isn't quite good enough to do that. The following theorem gives us an alternative definition of linear dependence that generalizes nicely. Theorem 8.4. Let V be a vector space over a field F and let little v and W be in big V. Then V and W are linearly dependent if and only if there are J, K, and F not both 0, such that JV plus KW is equal to 0. Let's prove this. Let V, W be in V, and suppose that V and W are linearly dependent. Then one vector is a scalar multiple of the other. Without loss of generality, we may assume that there's a C in F with V equal to CW. In other words, V is a scalar multiple of W using the scalar C. Then we have 1V plus -C times W is equal to 0. So if we let J equal 1 and K equal -C, then JV plus KW equals 0, and the weight J is equal to 1, which is not 0. Now, suppose that there are J, K, and F not both 0, such that JV plus KW is equal to 0. Without loss of generality, let's assume that J is the one that's not 0. Then we have JV equals -KW, and so V equals -K over J times W. We could divide by J here because we know it's not 0. So V is a scalar multiple of W. Therefore, V and W are linearly dependent. Let V be a vector space over a field F. Let little v1, v2 through vn be in V, and k1, k2 through kn be in F. The expression k1 v1 plus k2 v2 plus ... plus kn vn is called a linear combination of the vectors v1 through vn. We call the scalars k1 through kn weights. Let's look at an example. Let V equal R3 be the set of ordered triples ABC such that A, B, and C are real numbers. Let that be the vector space over R with the usual definitions of addition and scalar multiplication. Let V1 be the vector 1, 0, 0, V2 the vector 0, 1, 0, and V3 the vector 0, 0, 1. Let K1 equal 3, K2 equal -5, and K3 equal 6. We have K1 V1 plus K2 V2 plus K3 V3 equal to 3 times 1, 0, 0 minus 5 times 0, 1, 0 plus 6 times 0, 0, 1, which is 3, 0, 0 plus 0, -5, 0 plus 0, 0, 6, which is equal to 3, -5, 6. It follows that the vector 3, -5, 6 is a linear combination of the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1, with weights 3, -5, and 6, respectively. If V1 through Vn in V, where V is a vector space over a field F, then the set of all linear combinations of V1 through Vn in V is called the span of V1 through Vn. Symbolically, we have span of the set of V1 through Vn is equal to the set of K1 V1 plus K2 V2 plus dot 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 plus Kn Vn, such that K1 K2 through Kn is in the field F. Let's look at an example. In the previous example, we saw that 3, negative 5, 6 can be written as a linear combination of the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. It follows that 3, negative 5, 6 is in the span of the set consisting of the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. Theorem 8.5. Let V equal Rn equal the set of n tuples k1 through kn, such that k1 through kn are real numbers, be the vector space over R with the usual definitions of addition and scalar multiplication. Then the span of the set consisting of the vectors 1, 0, 0 through 0, 0, 1, 0 through 0, and so on through 0, 0, 0, 0, 0, 0, 0, 1 is equal to the whole space Rn. Proof. Let V be in the span of these n vectors. Then there are weights k1 through kn in R, with V equal to k1 times the first vector plus k2 times the second vector, and so on, plus kn through the nth vector. So we have V equal to the vector k1 0 0 0 0 0 plus 0 k2 0 followed by all zeros plus through all zeros except for the last entry being kn, which is the vector k1 k2 through kn. Since k1 through kn are real numbers, we have that V equals the n tuple k1 through kn in Rn. Since V in the span of these n vectors was arbitrary, the span of these n vectors is a subset of Rn. Now, for the other way, let V be in Rn. Then there are weights k1 through kn in R, with V equal to the vector k1 through kn, which could be split up as the vector k1 followed by all zeros plus 0 k2 0 followed by zeros plus dot 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 plus all zeros followed by kn, which is k1 times 1 followed by all zeros plus k2 0 1 0 followed by all zeros plus dot 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 plus kn all zeros followed by 1. Since we have expressed V as a linear combination of these n vectors, we see that V is in the span of the set consisting of those n vectors. Since V in Rn was arbitrary, we have that Rn is a subset of the span of the set consisting of those n vectors. Therefore, the span of the set consisting of those n vectors is equal to Rn because each of those sets is a subset of the other one. If V1 through Vn in capital V, where capital V is a vector space over a field F, then we say that V1 through Vn are linearly dependent if there exist weights K1 through Kn in F with at least one weight non-zero, such that K1 V1 plus K2 V2 plus dot 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 plus Kn Vn is equal to 0. Otherwise, we say that V1 through Vn are linearly independent. A couple notes. V1 through Vn are linearly independent if whenever we write K1 V1 plus K2 V2 plus dot 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 plus Kn Vn equals 0, it follows that all the weights K1 through Kn are 0. We will sometimes call the expression K1 V1 plus K2 V2 plus dot 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 plus Kn Vn equal to 0 a dependence relation. If any of the weights K1 through Kn are non-zero, then we say that the dependence relation is non-trivial. Let's look at some examples. The three vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1 are linearly independent in R3. To see this, note that we have k1 times 1, 0, 0 plus k2 times 0, 1, 0 plus k3 times 0, 0, 1 is equal to k1, 0, 0 plus 0, k2, 0 plus 0, 0, k3 equals the vector k1, k2, k3. Therefore, k1100 plus k2010 plus k3001 is equal to 0, 0, 0 if and only if the vector k1, k2, k3 is equal to the vector 0, 0, 0, if and only if k1 is 0, k2 is 0, and k3 is 0. A similar computation shows that the n vectors, 1 followed by all zeros, 0, 1, 0 followed by all zeros, dot, 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 all zeros followed by 1, are linearly independent in Rn. The vectors 1, 2, 3, negative 2, 4, 3, and 1, 10, 12 are linearly dependent in R3. To see this, note that 3 times 1, 2, 3 plus negative 2, 4, 3 equals 3, 6, 9 plus negative 2, 4, 3 is equal to 1, 10, 12. And therefore, 3 times 1, 2, 3 plus negative 2, 4, 3 minus 1, 10, 12 is equal to 0 vector. This gives us a non-trivial dependence relation because we have at least one non-zero weight. In fact, all three weights are non-zero. The weights are 3, 1, and negative 1. If V1 through Vn are in capital V, where capital V is a vector space over a field F, then we say that the set V1 through Vn is a basis of V if V1 through Vn are linearly independent and the span of the set V1 through Vn is equal to V. Let's look at some examples. In the previous example, we saw that the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1 are linearly independent in R3. By theorem 8.5, the span of the set of these three vectors is equal to R3. It follows that the set consisting of these three vectors is a basis of R3. Similarly, the set consisting of 1 followed by all zeros, 0, 1, 0 followed by zeros, dot, 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 all zeros followed by 1 is a basis of Rn. In the previous example, we saw that the vectors 1, 2, 3, negative 2, 4, 3, and 1, 10, 12 are linearly dependent in R3. It follows that a set consisting of 1, 2, 3, negative 2, 4, 3, and 1, 10, 12 is not a basis of R3.